Hi, my name is Vishal, and I'm going to kick off my YouTube channel, which is going to focus on what I'm learning in machine learning with this video on negative prompting. And negative prompting in Stable Diffusion is a concept we learned about in part 2 of the FastAI course. I think it was lesson 10. And one of the homework assignments for that lesson was for us to implement negative prompting given the boilerplate code for Stable Diffusion as part of that lesson. So that's what I'm going to do in this video. I've already run the imports and pip installs. We're going to use the diffusers library. We're going to use scheduler, autoencoder, which is the VAE. We're going to use a UNet. That's going to do the actual noise estimates. And then I've also imported the Stable Diffusion pipeline because I want to show how negative prompting works built in to the diffusers library. We also have our text tokenizer and the text model, which is going to convert our tokens into embeddings, some image processing stuff, and then here we have the particular models that we're using. It's the same as what's provided in the course. The particular scheduler that's being used and the start and end values for the scheduler. And then we are doing a image height and image width of 512 pixels. So on the left here is a guide of outline of what this video is going to involve. I'm going to start by walking through line by line the code for basic generation using the Stable Diffusion loop. And it's going to be using classifier-free guidance. Then I'm going to go into the negative prompting implementation and start by explaining the main concept at play. And then I'm going to run through some different guidance scale values and see how it varies the image generation. And then I'm going to show an example using the built-in diffusers implementation. The link to the source code or the diffusers library that shows their implementation is in the video description, and it's very similar fundamentally to the implementation that I've come up with here. Okay, so let's go through our basic generation. The first thing we need to do is encode our text, and to do that we need some text to encode. So I'm going to do Labrador in the style of Vermeer, and this is the prompt that we use in the lesson. So that's that. And then we're going to set our batch size to be the length of the prompts that we have. So we only have one batch size here. We have batch size of 1 because we have one prompt. So that's sort of some of the initial setup. The next thing that we're going to do is we are going to define the maximum length of our prompts. So we're going to take the tokenizer and we're going to set it to the attribute, which is model max length. Oops. And if we look at max length, it should be 77, which is how many tokens there are going to be in our token embeddings. So now comes the part where we are going to use the tokenizer. And as inputs, we're going to give it our prompts, which is a list of strings. These parameters that I'm listing here, these are just what are used in the course video or in the course code. So I'm just basically following what is used there. And there we go. So that's max length. We have this truncation parameter. And then we want to return tensors as PyTorch tensors. Okay, so this should give us a bunch of input IDs, which are our tokens, and we can see that there's a starting token and an ending kind of padding token, and then we have our tokens that actually correspond to Labrador in the style of Vermeer. Okay, cool. So that gives us our tokens. Once we have our tokens, we're going to encode them into embeddings using our text encoder. So we pass it the input IDs, and we make sure that the IDs are on our GPU. And we're going to take the first value that's returned, and we're going to do half precision. So this should be text encoder is not defined. Oh, That's because I have to spell it out. Cool. So we have one bat size, or a bat size of 1, because we have one prompt. There are 77 tokens, and this has now projected those tokens into 768 dimensions, which is our embedding space. So this entire process that we did, I'm just going to wrap this into a function that's going to be called text_enc, and we're going to take prompts, and we're going to take a max length, and I'm basically going to take of the code that we did above, and we're just going to take each of these steps. So I'm going to assign the max length. I'm going to then grab this line, which is going to tokenize our prompts, and then what I'm going to return is I'm going to return the actual text embeddings. So I'm going to run that, and then just make sure that, whoops, just make sure that this is giving us the right shape, which it is. Okay, cool. So in classifier-free guidance, we have the text that we want to condition our generation with, which is like our goal, which is Labrador in the style of Vermeer. And then we also have unconditioned text that we're trying to move away from. It's sort of like a starting point for the model. Some text that represents like a good random starting point. And so what we're going to use for our unconditioned prompt is just an empty string. So I'm going to call text_enc, and I'm going to pass it an empty string inside of a list times bat size, and I want to make sure it's the same shape as my prompt embeddings, my conditioned embeddings. So I'm going to these are going to be my same sized embeddings, but they represent an empty string. This is basically like a starting point. So we're starting from some representation of random text, which is just an empty string. Okay, so the last step I'm going to do is I'm going to concatenate my unconditional embeddings and my conditional embeddings, and then I'm going to check the shape. And the reason we do this is so that we don't have to do 2 passes of in the UNet model. We're just going to concatenate this so that we just have to do 1 forward pass through that model. Okay, great. So this gives me my embeddings. So we've done our first step. The next step is we want to now create a starting point, a random noisy starting point for the image generation. So I'm going to do the first thing I'm going to do is set my seed, and I found that a seed of 20 kind of gives me a result that is desirable. And so I'm going to set my seed with this method, which returns a generator. Cool. Now I'm going to actually create my latents, which are just a random set of tensors with the shape of bat size, the number of channels, let's see, UNet in channels, 1/8 of my height and 1/8 of my width, because that's what the VAE is going to expect. So I run this and I see that now I have one noisy image that has 4 channels, and each channel is 64 by 64. So this is kind of creating my kind of template for the latents that I'm going to have. Okay, so those are my noisy latents, and they're just random numbers at this point. So we're starting with a random number, a random set of noisy latents. Now we're going to actually do the diffusion. So we have our unconditioned and conditioned text embeddings. We have our starting point for our latents. First thing we're going to do is define how many steps. And so in the course example, we use 70 steps. I think the diffusers model or pipeline uses 50. I'm going to set the time steps for my scheduler to 70 so that it knows how much noise to add. This following line that I saw in the course, this is kind of setting the correct amount of noise to match the time steps that we have set. There's a couple ways to do this. You can either multiply by scheduler, I think it's scheduler.init sigma or something. It's like whatever the initial noise value is. In the course, they used 15, and when I tried these two different values, the value of 15 just kind of had a better output, seemed like a more coherent output, so I'm just going to stick to using 15. I think the actual value is like 14 point, something. So this doesn't change the shape, but it is applying this initial kind of noise factor to the latents. I need to get the first time step because I need to pass the time step to my unit. So I'm just going to pick the first time step, which is going to be 999. I think it starts at it's 1,000 on the scale of 1,000 time steps divided by the 70 increments that we chose. And now I'm actually going to pass kind of one more setup phase that I need to do. I don't know too many details about scale model input, but I do know we have to run it before we can pass this into our unit. This times 2 for this list of latents. The reason we do that is because we have an unconditioned prompt as well as a conditioned prompt, so we have to have 2 of these. Alright, so if we look at the shape, it's going to be similar to our original latents, but now there's just 2 of them. Okay, so we have everything we need to give to our unit. So we're going to make sure that we're not calculating any gradients with this step. What we're going to get out of the unit are, in the latent space, the noise estimates for the unconditioned prompt, the empty string, and that's U, and the conditioned text, our goal, which is T. And I'm going to call my unit, so this is the forward pass. I'm going to give it my latents. I'm going to give it my time steps, or a single time step. I'm going to give it my text embeddings. What I want back is the sample, and it's we doubled up on everything because we're doing classifier-free guidance, so I want to split it into 2. So if everything was correct, we're going to get back the same size as our input latents that we had, except now this one's conditioned on empty string, so it's unconditioned. This one's conditioned on our text. Great. So that kind of gives us our 2 outputs. Next, we're going to do the classifier-free guidance step. So I'm going to set my guidance scale to 7.5, which seems to work well. And my final prediction is going to be the unconditioned prompt plus my guidance scale times the difference between the 2. So this is basically pushing the prediction from the unconditioned towards my conditioned, and it's using this guidance scale as a way to kind of scale up this difference. Something that I'm planning to do in a different video is actually look at these values of T and U and see, like, how close are these values to start with in the embedding space, and that kind of helps give me some intuition on why the G values are relatively large. So I do this. This should not change the shape. I still have my latents in 4 by 64 by 64 dimensions. Okay, cool. So this gives me my noise estimates using classifier-free guidance. And the last step I'm going to do is I'm going to say, subtract the appropriate noise given the time step we are at, given these noise estimates, and given our original latents, which were purely random. And this is the syntax that we use for that. And again, this should have the same shape. Okay, so that in total is the kind of full diffusion loop, or one step of the diffusion loop. What it would look like in the loop is as follows. So I'm just going to write down what we had from the course. So we're gonna iterate through all of our time steps, all 70 of them. We're going to grab this kind of preparation or input prep for our unit, and it's going to use the latents, the random ones at the very first step, and then every time it uses the previous step's latents and the given time step. We're going to grab our unit predictions, which we do there. We're going to grab our classifier-free guidance, and then we're going to grab the actual step, diffusion step, where we use our noise estimates and incrementally remove them from our latents, get our final image. So, and this should actually be up here. So this is our full loop. I'm not going to run it now. We will run it in a second when we look at the full pipeline. So we end up with these latents after one step of diffusion. So now what we're going to do is we're going to convert that back to image space. So we again use torch.nograd, and we're going to get back a tensor from our VAE, and we have to apply this particular factor that is dependent on the model, and we have to multiply our latents by that, and then we get the sample. And I'm just going to look at the shape. So this should be an image space. So now we have a batch size of 1, 3 channels for RGB, and now we're back to our 512 by 512 space. So that's in tensor form. We have to do a little bit of processing, which I'm going to type through here. We have one item in our batch, so I'm just going to take the 0th element of that tensor. The variational encoders kind of clamps this information from -1 to +1, so we're going to bring it back to the 0 to 1 space by dividing by 2 and adding 5. We're going to clamp it between 0 and 1. We're going to take it off of the GPU, and we're going to switch the dimensions around so that we can visualize it more easily. And so if we look at this shape, this is now 512 by 512, and we have 3 images. And the last step for generating our image is we're going to use the pillow library, and we're going to get this back into, instead of 0 to 1, it's going to be 0 to 255. And looks like we're going to do some rounding. We want it as a integer. And then I think that's it. So this should now show us an image. And at this stage, we've only done one step. I didn't run the entire loop, so this is just one step of the diffusion loop, and it's just random noise. But it's an image, and our process works so far. So I'm going to wrap this into the same code that we did in the fastai course. So this basically takes our line here, and in my case I had one image, but we would want to process all images in the batch, so I'm going to just take the entire t value here, and then what I'm going to return is this operation. And that should do it. So if I run this and I take the first image, this should hopefully give me that same random noise. Okay, so it looks like something is funky there. So let's run this again. This is that. And I think I see what the issue is. I think what I actually have to do is I have to pass it. Okay, yeah. So yeah, this T is, I said it incorrectly. It's not the entire batch. It's actually a single image. So okay, cool. So this gives me my desired result. And now that we've seen the entire process, I'm going to put that all into a function called makeSamples. This is the same function that you will see in the fastai course. So I'm going to start all the way at the top. So I'm going to get my batch size, and I'm going to then encode. Let me see what we do here. Yeah, so I'm going to encode my prompts. Whoops, let's just run this here. So we're going to encode my prompts into text embeddings. I'm going to then get my unconditional embeddings and put that here. And then we're going to concatenate the two. And let's just use our navigation. So we're going to concatenate the two, which was this line. Since I'm navigating, I'm just going to put this helpful thing here. Okay, so we're going to concatenate the two. That's going to give us our embeddings. Then I'm going to set the manual seed. So if we have a seed, we're going to set it. We're going to grab this line of code to get our latents. And I'm actually going to try to expedite this process a bit. So I want to get my time steps as well. I want to do the multiplying by 15 step. And that should give me everything I need for my latents. And then finally, what we're going to do is we're going to just take the loop that we have. So that was, I think, somewhere here. And then the final piece that we're going to add is decoding our latents. And we're going to return. So just to summarize, and I'll put some comments in here, this is prepare text embeddings, and really this seed is associated with latents. So prepare initial noisy latents, and then self-explanatory, but I'll just say diffusion loop with classifier-free guidance. And our inputs are going to be our prompts, our guidance scale, the seed that we want to use for the random noise at the start, and then the number of steps. This should run through our number of steps. We should get our classifier-free guidance, remove that noise from our latents, do that until we get through our 70 steps, and then this should give us back our decoded tensor. So this is our makeSample code, and yeah, so let's do one more step here, which is, let's take a look at my prompts. So Labrador in the style of Vermeer. I'm going to call my makeSamples with my prompts, and everything else I can keep because I want 7.5 guidance scale. I want a seed of 20. I want 70 steps. So I'm going to run that, and this should be maybe 10 seconds or so. This runs through, and this should give me the right shape, which is 3 by 512 by 512. And then since it's a batched set of images, I'm going to iterate through and do that, and we should see, yeah, so we see this particular Labrador in the style of Vermeer. And this is correct. This is the input or the output I get for this particular seed. Okay, so let me copy this code because I'm going to define examples. And the basic idea, that's why I've put this up here, is that negative prompting is the same concept as classifier-free guidance. But instead of going from an unconditioned prompt and moving towards our conditioned prompt, we're simply going to move away from our negative prompt and move towards our conditioned prompt. So U in this case, without negative prompting, is an empty string. With negative prompting, U is just going to be the embeddings or the noise estimates corresponding to our negative prompt embeddings. So I'm going to change very little in my make samples. I'm going to say negative prompt as a default. So my default version is going to be regular classifier-free guidance. And I'm going to pass that negative prompt into this list. And that's it. That's all I change, because these unconditioned embeddings is either going to be an empty string or it's going to be whatever prompt that I pass it. Everything else stays the same, because the core concept here is that, this is the same for negative prompting. And if you look at the diffusers implementation, at least my interpretation of it was that it was, very similar conceptually. So I'm going to run this here. And so if I look at my prompts, I have that kind of goal that I want. The negative prompt I'm going to set is going to be blue. And the idea is that I want to remove the blue from my image. And I think what I can do now is I can copy this code up here where I was making my images. And I'm going to remove this because we've seen the shape. And I'm just going to copy this code. So I'm going to first run, just make sure I have this run. So I'm going to run the default version, which should be the same. So I'm not giving it any negative prompt. This should be the same because the seed is the same. This should give us the same Labrador with the blue background. And it does. Great. So now when I run this again, what I'm going to do is I'm going to give it a negative prompt, blue. And now I'm going to run this. Nothing changes in the code except now it's encoding my unconditional embeddings as blue instead of an empty string. And great, it has removed the blue, and I guess it's leaned into more of the red. You'll notice that it's not exactly the same. So this dog is kind of standing upright. This dog is now suddenly laying down. But I found this to be the case even when using the diffusers implementation, which we'll see in the end. So this is great. We're moving right along. One experimentation I like to do, and I like to do this with anytime I do anything with diffusion because it's so visual. I love to just try to iterate on different factors. In this case, guidance scale is a factor we can iterate on, and you make a GIF animation or kind of look at the images. It's just a really fun thing for me to kind of visualize some of these things. So I'm going to create a set of images now, and I'm going to go through each of my guidance scales. And even though I have a batch size of 1, I still have to kind of iterate through my make samples output. I'm going to put a negative prompt of blue, and guidance scale is going to be G, and my seed is already 20, so I don't need to do that. So this should take, maybe a minute, and it should run through 1, 2, 3, 4, 5, 6, 7 different images. So I should get 7 different images. Okay, so I have my 7 images. I'm just going to make sure that is the case, and I do. The following line I found was super cool. So I can take the first image, which is a pill image, and I can call save, and I'm just going to call it guidance scale.gif, and some of these parameters I'm not 100% sure what they mean, but this is what works. And I'm going to append all of the subsequent images after the first one. And I think this is an equals. And I want 100 milliseconds. Let's do 200 milliseconds for each image. And we don't want it to loop because it'll already loop. And this should, if we look on the side here, this should give me, yeah, okay, cool. So that's there. And then if there's an easier way to display GIFs in a notebook, please drop that in the chat. Otherwise, I'm going to go with this concept that at least works, which is it's going to take, let's see, it's going to open guidance scale .gif, and it's going to read it, and I think this should do it. So let's see if that works. That's because I misspelled that. Cool. So we can kind of see, you know, at the very early guidance scale, it's a kind of a very random image of a dog. And then as the guidance scale increases, we get, you know, a much more kind of match in terms of structure and composition with the original image. And we can see that, you know, our blue is somewhat being removed. At higher guidance scales, kind of goes towards blue again, so that's kind of interesting. To look at some of the individual images, so here's the guidance scale of 1. So as you can see, it has a dog, but it's still very random. Here is our very final image, which is a guidance scale of, I think it was 14. Yeah, 14. Yeah, I mean, that looks okay. It's not terrible, but I think the 7.5 guidance scale does look kind of more realistic and accurate, or matching the kind of goal that we want, that it's like more of a realistic painting. This one looks a little bit like a cartoon, you know, and that's a trend I've noticed with guidance scales. As your guidance scales get larger, that it tends to abstract away some of the details. So that's our kind of end-to-end implementation. The last thing I'm going to do is I'm going to take a look at the diffusers library and see what it looks like. So this is comp.viz, stable. I should probably have this ready to copy and paste, but we're going to roll with this for now. The variant is half precision, and the torch D type is float 16, and we want this on our GPU. So this should give me the pipeline, and it'll take a second to download. So I'm going to use the same manual seed as the course, which is 1000, because it makes a very nice result. The prompt is just the same prompt that we had. I'm just going to take the first one, and then I'm going to pass that prompt and then get back the image. So this should be a very beautiful Labrador in the style of Vermeer. And notice how they're only doing 50 steps. And yeah, so this is what we should expect. So notice the blue in the hat and in this kind of scarf. So if I take the same code, and what I do is I give it a negative prompt of blue, this should do a pretty good job, or a really good job, of removing the blues from the image. And it does. So now instead of a blue hat, it's a black hat. Instead of a blue scarf, now, it's this beige kind of coat that this Labrador is wearing. It's not exactly the same. The head of the Labrador and the ear shapes have kind of changed, but it's pretty good. And that is something I wanted to highlight is that, oops, depending on the seeds that you give, it's going to give you different results. So, if I use seed 20, we'll see that it's, a very, very different image of a Labrador. And then in fact, it has other artifacts that are not requested in the image. So we have this person here. They do have a lot of blue, so we should expect that to be removed. So if I copy my negative prompt code down here, and I give it the seed of 20, this is where kind of the success of negative prompt is a bit fuzzy, because did it remove blue? Yes, it did, right? This person's blue dress is no longer there. But it also drastically changed the image. So it's really not the same image. It's just a completely different image where it does have a Labrador, but it doesn't have blue. So I found this to be interesting that even with the diffusers implementation, and this is probably dependent on the model that we're using, negative prompting is very dependent on the seed. So if you don't start with the right seed, you don't get the right results. Okay, so that is it. I'm going to drop the link to my blog post on this topic, as well as the diffusers implementation, link to the particular line in the source code that I wanted to share with everyone. My blog post also goes into some other failed attempts that I tried for implementing negative prompting, so check that out if you're interested. And yeah, I will just wrap it up here and say I'm excited to put more videos out here and learn more things in machine learning. So thanks for watching.